High above Neptune, a white cloud is moving. 1 hour later, it has crossed hundreds of kilometers. An hour after that, it has moved again. The planet beneath it looks unchanged. The same deep blue, the same distant, silent sphere hanging in darkness. A single photograph makes Neptune look almost motionless. So, place 2 photographs side by side. The planet is still blue, still quiet, but the cloud is somewhere else. Add another image. It has moved again. Then another. The clouds keep circling while almost everything else appears frozen. Speed up the sequence, and the planet comes alive. Bright white clouds sweep around Neptune in ribbons thousands of kilometers long. They are not chasing one storm. They are riding the atmosphere itself. Hour after hour. Day after day. The clouds change. The motion continues. When Voyager 2 passed Neptune in 1989, it photographed those clouds often enough to measure their movement. The distance between 2 images was known. So was the time. That was enough. Some winds were moving faster than 2,000 kilometers an hour. Decades later, telescopes on Earth watched Neptune again. The clouds had changed. The storms had changed. But the great paths through the atmosphere were still there, carrying new clouds around the planet at extraordinary speed. And only after that motion becomes visible does another number begin to matter. Neptune orbits nearly 5 billion kilometers from the Sun. Its upper atmosphere sits near 59 degrees above absolute zero, making it one of the coldest atmospheric environments in the solar system. The clouds keep racing. On Earth, wind usually begins with sunlight. The ground warms. The air above it follows. Neptune seems to begin somewhere else. The sunlight is faint. The atmosphere is frozen. Yet the motion is already there. Look at one photograph, and Neptune seems still. Place another beside it, and the clouds have moved. The planet never looks fast. Its atmosphere never stops. The movement comes first. The explanation has to catch up. At first, the wind speed sounds like the whole mystery. More than 2,000 kilometers an hour. Fast enough to circle a planet in only a few hours. It is an easy number to remember. The harder question is why winds like that should exist at all. On Earth, the energy source is obvious. Sunlight reaches the ground heats the air. By afternoon, the atmosphere is carrying that energy away through wind, clouds, and storms. Energy arrives. Then the air moves. Neptune follows the same sun, but from much farther away. At Earth, a square meter facing the sun receives about 1,360 watts of energy. At Neptune, it receives about 1.5. The sunlight there is roughly 900 times weaker. The clouds do not care. They keep crossing the planet. The same broad bands keep circling the atmosphere. The sunlight shrinks. The motion does not. Picture noon on Earth. Now drain almost all the brightness from it until daylight barely feels like daylight. That is the sunlight available to Neptune's upper atmosphere. And still the clouds move. Perhaps weak sunlight works differently that far away. Perhaps Neptune's atmosphere needs very little energy. Perhaps the numbers only look incompatible. But place them together, very little sunlight reaches the planet. Its upper atmosphere remains close to 59 degrees above absolute zero. Its winds still exceed 2,000 kilometers an hour. Nothing changes when the measurements are combined. The sunlight does not grow stronger. The atmosphere does not grow warmer. The winds do not slow down. The familiar sequence begins to fail. On Earth, sunlight arrives first. Then the atmosphere responds. On Neptune, the atmosphere is already moving. Whatever drives those winds no longer fits comfortably inside the idea that sunlight alone patterns planetary weather. The photographs remain exactly the same. The clouds still race around the same blue planet. But now they carry more than motion. They carry evidence. Not yet of what powers Neptune. Only of where the answer cannot be. It is not waiting above the clouds. It has to be somewhere else. The answer arrived as another measurement. One number described the winds. Another described the sunlight. A third described the planet itself. Every planet absorbs energy from the sun. Every planet also releases energy back into space. If those amounts are equal, the planet is simply returning what it receives. But if more energy leaves than arrives, something inside the planet must be adding to the total. Infrared observations showed exactly that. Neptune releases far more energy than sunlight alone can supply. Roughly 2.5 times more. The clouds did not change. The sunlight remained just as weak. Only one new number was added. And the entire picture shifted. The winds were never the first clue. They were simply the easiest clue to see. The missing energy had been there all along. Not above the clouds. Inside the planet. No telescope can look down and watch that energy rise from Neptune's interior. It does not appear as a bright point beneath the atmosphere. It escapes quietly. As heat. Every second, Neptune radiates that heat into space. Infrared instruments do not need to see the deep interior. They measure the energy leaving the planet, then compare it with the energy arriving from the sun. The two numbers do not balance. Something inside Neptune is continually adding energy to the system. Watch the clouds again. They no longer look like impossible weather. They look like the visible surface of something much larger. The atmosphere is moving because energy is moving. And not all of that energy comes from above. Some of it is rising from below. The same clouds trace the same paths around Neptune. The same bands circle the blue sphere. The same winds cross thousands of kilometers. But now the motion is connected to something invisible. Not sunlight. Something deeper. One measurement revealed the speed. Another weakened the simplest explanation. This one replaced it. Neptune is not waiting for enough sunlight to drive its atmosphere. The planet is supplying energy of its own. The winds no longer point toward the sun. They point inward, toward a world that has been releasing heat for billions of years. Place the photographs side by side again. The clouds have moved. Now place one more image beside them. Not a photograph. An infrared map. For the first time, the heat and the motion belong to the same picture. But heat alone is not enough. Put a pot of water over a flame. The water does not begin flowing smoothly in one direction. It boils, bubbles rise, currents collide, the whole thing churns. Neptune should seem similar. If heat is rising from deep inside the planet, why is the atmosphere not simply chaotic? Why do the clouds keep returning to the same broad paths? Why do enormous rivers of air survive for years, even decades? The photographs answer before the models do. Place Jupiter beside Neptune. Jupiter's atmosphere is crowded. Storms grow beside other storms. Clouds twist through turbulent belts. the planet rarely looks still. Now return to Neptune. Much of the blue planet appears almost empty. Long stretches of atmosphere show little visible disturbance. The bright clouds are fewer. The bands look cleaner. The motion seems less crowded. That difference is not merely visual. It changes what happens to energy moving through the atmosphere. On Earth, sunlight constantly stirs the upper layers. Warm air rises, cool air sinks. Small, turbulent currents form almost everywhere. They move energy in every direction. They also slow larger flows. Neptune receives very little sunlight. Its upper atmosphere remains cold and comparatively stable. The broad rivers of air encounter far less of the constant mixing found in warmer atmospheres. Heat still rises from inside the planet, but it rises into an atmosphere that offers surprisingly little resistance. The energy keeps moving. So do the winds. Neptune's atmosphere is not behaving like boiling water. It is closer to a river moving through a wide, quiet valley. The river still carries enormous energy. It simply loses less of it along the way. That changes what the clouds have been showing from the beginning. They are not racing because Neptune is unusually violent. They are racing because very little is slowing them down. Watch them again. The white streaks cross the same blue world. The same wind patterns circle the planet. But now the movement belongs to a complete system. Energy rises from below. The atmosphere carries it outward. Weak sunlight leaves the upper layers comparatively undisturbed. The great rivers of air keep flowing. The clouds make those invisible currents visible. Place the first photograph beside the last. The cloud has moved. The measured speed has not. More than 2,000 kilometers an hour. At first, that number seemed to contradict everything a frozen world should be able to do. Now it describes exactly what this atmosphere can become. The mystery was never simply the speed. The speed was the visible shape of an engine operating beneath the clouds. When Neptune first came into view, its winds looked like the mystery. Now they look closer to the answer. The clouds have not changed. They still cross the same blue atmosphere. They still move faster than any sustained winds measured elsewhere in the solar system. What changed was the picture around them. One measurement showed how fast they moved. Another showed how little sunlight reached the planet. A third showed that Neptune releases more energy than it receives. A fourth revealed an atmosphere where that energy can travel with remarkably little resistance. Each observation preserved the one before it. Together, they changed what the clouds meant. At first, the winds seemed impossible. Now they seem almost inevitable. Neptune is not breaking the rules. It is following rules that were hidden beneath the simpler ones. It feels natural to assume that distance from the sun determines how active a planet's weather can be. Closer means warmer. Warmer means more energy. More energy means stronger winds. That picture works surprisingly well until Neptune enters it. There, the sunlight weakens. The atmosphere grows colder. The winds keep moving. Not because Neptune ignores physics, because planetary weather has never depended on sunlight alone. Every atmosphere belongs to a larger energy system. Some worlds receive almost everything from their star. Others keep drawing on energy stored deep inside themselves. The atmosphere reveals where that energy goes. Look at Neptune again. From billions of kilometers away, it still appears calm. A blue sphere suspended in darkness. No single photograph captures the speed of its atmosphere. No still image shows rivers of air crossing the planet faster than sound. Place 2 photographs side by side. The clouds are already somewhere else. Add another. They have moved again. The planet never seems to hurry. Its atmosphere never rests. This quiet blue world is not hiding violent weather. It is showing what planetary weather can look like when the power comes from within. The clouds never announce where their energy came from. They simply kept moving. Long enough for the measurements to catch them. Long enough for the picture to change. The winds stayed the same. Only their meaning changed. And the measurements continue. The clouds circling Neptune today are not the clouds Voyager 2 saw in 1989. The bright storms have changed. Some vanished. Others formed in new parts of the atmosphere. The great dark spot that greeted Voyager is gone. New storms have appeared where old ones once dominated. The weather changes. The engine beneath it continues. Ground-based observatories still watch Neptune. So does the Hubble Space Telescope. Each image adds another point to a record now stretching across decades. The goal is no longer simply to find faster winds or stranger storms. It is to test the pattern. Is Neptune's atmosphere still behaving like the one those earlier measurements described? Again and again, the broad circulation returns. The details change. The pattern remains. That is often how planetary science advances. Not through one dramatic discovery, but through measurements that keep agreeing long after the surprise is gone. Neptune has become one of those tests. Its atmosphere is not merely something to observe. It is a way to test new ideas about how giant planets move energy from their interiors into space. Parts of that story remain unresolved. The exact origin of Neptune's internal heat is still an active area of research. Some models point to heat left from the planet's formation. Others examine gravitational separation deep inside Neptune. Still others explore how materials behave under pressures that cannot be reproduced on Earth. The measurements do not yet choose among them. They tell us only that the heat is there. But that uncertainty does not reopen the mystery we began with. The original question was not how Neptune created its internal heat. It was simpler. Why does one of the coldest planets have the fastest sustained winds in the solar system? That picture has changed. The clouds did not slow down. The planet did not grow warmer. The sunlight did not grow stronger. Instead, the atmosphere became part of a larger energy system. The winds were never fighting the cold. They were revealing what the cold had hidden. Look once more at the same blue planet. It still seems distant. Still quiet. Almost motionless. Place 2 photographs side by side. The clouds are already somewhere else. Place another beside them. They have moved again. The photographs never explain why. They do not need to. The movement was there from the beginning. Only our picture of it changed. Neptune no longer looks like a frozen world that somehow learned to outrun every other planet. It looks exactly like what it has been all along. A planet carrying its own energy upward. One cloud at a time.